Welcome to part 2 of the video lesson on instantaneous rate of change. In part 1, we went through the definition. We looked at the limit of the difference quotient, and we looked at this formula to find the instantaneous rate of change. And for this function, we calculated the instantaneous rate of change. So we went through the work and the formula, and we simplified and did the algebra, and we plugged in the given x value, and we found that the instantaneous rate of change for that function at this point was -6. So what does that mean? Well, remember that when we found the average rate of change, we were finding the slope between 2 points on a function. And the closer together those 2 points were, the more accurate was that rate of change, that slope, looking at the curve or the function. When we're finding the instantaneous rate of change, what we're really finding is at that exact point. So this is the function in question, the -2x squared plus 2x plus 1, and the point 2, -3. At that point, what we have found is that this -6 represents the slope of the tangent line, the line that just touches the curve at that point. So when we found the average rate of change, depending on how big an interval we found, we could have found a rate of change of -7 or -8, something that is close, but this is the exact slope at that exact point of the tangent line, the line that just touches at one point that curve. So that's what the instantaneous rate of change means. Another way that you could find it, as opposed to the previous example, if I asked you to find the instantaneous rate of change of a simpler function, f of x equals x squared at this given x value, I don't have to do it all algebraically. Remember that in the last example, we looked at point 1 being just x, comma, f of x, and point 2 being x plus h, comma, f of x plus h. But here I could plug in, instead of x, the point -3. And if I plug that in, I would find that f of -3 is -3 squared, that's 9. And I could call my point 2 -3 plus h instead of x plus h, and -3 plus h all squared when I plug that in. So I can do this instead of purely algebraically with all the x's, I can do it with numbers as well. I can still find my instantaneous rate of change by taking the limit as h goes to 0 of this quotient of the difference. And I'll still have terms that will cancel out, and I'll still be able to factor out an h. So it turns out that this limit is the same as this limit, and that's just -6. I don't have to plug in my x value at the end. I could have plugged it in at the beginning. And that means that the instantaneous rate of change of that function at that point is -6. That is the slope of the tangent line. And that brings me to the next point, which is that I can ask you to find the equation, not just the slope. If you're asked to find the equation of a tangent line, and the wording of a question will look like, find the equation of a tangent line to a certain function at a certain x value. In general, the steps that you would go through would be, first, to find the instantaneous rate of change. That's going to be the slope. And 2, you'll plug in the known point, x and y, and we can find the equation of that line. We've already done the work for this function to find the instantaneous rate of change. It was above, we found it, it's -6. So all of that work. And though I just sort of wrote down the point, if you actually wanted to show the work to find that point, I would plug in -3 as my x value and find that my y value there is 9, so that's my point. And when I'm finding the rule of a line, I can use something that we learned back in grade 9. I can use the point slope form of the line. It's very fast to do. I'll just take this slope and this point, and that is the equation of the tangent line to that function at that point. Thanks for watching part 2.